Welcome to the lesson on the fundamental theorem of arithmetic. At the end of this lesson, you will be able to state the fundamental theorem of arithmetic. You will also be able to apply the fundamental theorem of arithmetic to calculate the prime factors, the HCF, and the LCM of any two composite numbers. Meet Mr. Number Maker. He's an old vagabond who's always on the move, but he has a special skill. Mr. Number Maker claims that he can produce any composite number you can think of. He uses a special set of tools to do so. Let us take a look at these tools. Oh, so Mr. Number Maker's tools are just a set of numbers, but these numbers are special. Observe carefully. What kind of numbers are these? All these are prime numbers. In fact, Mr. Number Maker has an infinite collection of all the prime numbers in his magical suitcase. Let's verify Mr. Number Maker's claim. Let's take a number. Any number. Say 1950, the year India adopted its constitution. Now, let's create a factor tree for this number using Mr. Number Maker's tools. Dividing 1950 by 2, we get 975. Dividing 975 by 5, we get 195. Dividing 195 by 5 again, we get 39. Dividing 39 by 3, we get 13. Now, 13 itself is a prime number, so we cannot factorize it any further. Thus, we see that 1950 can be expressed as a product of 2, 5, 5, 3, and 13, each being a prime number. What is true for 1950 is true for any composite number you can think of. Mr. Number Maker's claim is based on the fundamental theorem of arithmetic that states every composite number can be expressed or factorized as a product of prime numbers. Is there any other way to factorize 1950 using prime numbers? Let us see. Starting with 5 instead of 2, we get another set of prime factors for 1950. How are these factors different from the earlier ones? Note that the set of prime factors for 1950 still remains the same. Only the order of the prime factors has changed. This brings us to the complete statement of the fundamental theorem of arithmetic that states that every composite number can be expressed or factorized as a product of prime numbers, and this factorization is unique except in the order of prime factors. We can write the prime factorization of a number in the form of powers of its prime factors. Let us see how this is done. This is how it is done. Since 5 occurs twice in the prime factorization of 1050, its power is 2. Since 2, 3, and 13 occur once in the prime factorization of 1950, their power is 1. Mr. Number Maker has another interesting tip for you. He says that by expressing any two numbers as the product of their prime factors, you can easily calculate their highest common factor, that is, the HCF, and the lowest common multiple, that is, the LCM. Now, let us see how this is done. Let's put Mr. Numbermaker's tip to use. We already have the prime factorization of 1950. Now, let's take another number, say 2010, the year India hosts the Commonwealth Games. Let's find the prime factorization of 2010. Dividing 2010 by 2, we get 1005. Dividing 1005 by 5, we get 201. Dividing 201 by 3, we get 67, which itself is a prime number. Thus we see that 2010 can be expressed as a product of 2, 5, 3, and 67, each being a prime number. Since all the prime factors of 2010 appear once in its prime factorization, the part of each of them is 1. Now, let us consider the prime factorization of 1950 and 2010 together. Let us first find the highest common factor, or HCF, of these two numbers. To find the HCF of the two given numbers, locate the common factors in their prime factorization. 2, 3, and 5 are the common factors in the prime factorization of 1950 and 2010. Next, find the product of the terms containing the least powers of common prime factors of the two numbers. Let's see what this means. Since the powers of common factors 2 and 3 are 1 in both the cases, their power will remain 1 while calculating the HCF. The powers of common factor 5 in the prime factorization of 1950 and 2010 are 2 and 1 respectively. We will use the power 1 in calculating the HCF since it's the smallest power of 5. Thus, the HCF of the given numbers is 2 into 3 into 5 or 30. Now, let us first find the least common multiple or LCM of these two numbers. The LCM of two numbers is given by the product of the terms containing the greatest power of all prime factors of the two numbers. Since the greatest power of the common factors 2 and 3 are 1 in both the cases, their power will remain 1 while calculating the LCM. The power of common factor 5 in the prime factorization of 1950 and 2010 is 2 and 1 respectively. We will use the power of 2 in calculating the LCM since 2 is the greatest power of 5. The remaining prime factors 13 and 67 is the prime factorization of the two numbers who appear in the power of 1 in the LCM. Thus, the LCM of the given numbers is 2 into 3 into 5 square into 13 into 67 or 1,30,650. By now, we have expressed two randomly selected numbers as products of prime numbers. We have also used their prime factorization to calculate their HCF and LCM. Now, let us look at another interesting relation. Let us find the product of 1950 and 2010. First, let us find the product of the HCF and LCM of the given numbers. What do you observe? Note that the product of the given numbers is equal to the product of their HCF and LCM. This result is true for all positive integers and is often used to find the HCF of two given numbers if their LCM is given and vice versa. You've reached the end of this section. In this section, you learnt about the fundamental theorem of arithmetic. The theorem states that every composite number can be expressed or factorized as a product of prime numbers, and this factorization is unique except in the order of prime factors. You have also learned that the HCF of two numbers is equal to the product of the terms containing the least powers of the common prime factors of the two numbers. The LCM of the two numbers is equal to the product of the terms containing the greatest powers of all prime factors of the two numbers. and the product of two positive integers is equal to the product of their HCF and LCM.